Introduction to K nearest neighbors, KNN. So let's talk about the KNN. The K nearest neighbors, the algorithm is a foundation supervised machine learning technique widely used for both classifications and regression tasks. At its core, KNN predicts the outcome for a new data point by assessing a similarity to a point in a training dataset. The initiative method assumes that the similar data points tended to have the similar labels or values. So KNN offers a simple yet powerful approach to machine learning that makes no assumption about the underlying data distribution, placing it in the category of a non-parametric models. Because of its straightforward concept, KNN is often one of the first algorithms introduced in the data science education, allowing the practitioners to grasp the essential of instance-based learning. So the real-world applications of KNN spans various domains. It powers recommendation systems by finding users with the similar preferences, aid in image recognition by classifying objects based on the feature similarities, and supports the custom segmentations by grouping like consumers. It is versatility and interoperability make it a valuable tool in both research and industry settings. So what is KNN algorithm? Let's explain about it. So the KNN algorithm operates through a series of clear steps enabling it to classify a new instance or predict the continuous values effectively. So first step is choose the value of K. This represents the number of nearest neighbors to consider when making a prediction. Calculate distance. For new data point, distance to all data points are computed using specific metrics such as Euclidean, Manhattan, and Minkowski distance. Short distance and select neighbors. The training points are sorted based on the distance from new point and selecting the top K closest neighbors. Predict the output. So for classification, the most common classes among neighbors is assigned. For regression, the average or the weight average of neighbors values are predicted the target. The stepwise method allows a KNN to adapt to a different task while emphasizing similarity as a basis of prediction. The choice of K and distance metric critically influence its accuracy and making these parameters essential in turning the algorithm. Now let's understand what is distance metrics. KNN relies on measuring the distance between data points to determine similarities. Selecting an appropriate distance metric depends on the data nature and dimensionality. Common metrics include Euclidean distance, defined as the square root of the sum of the square difference cross features. It's ideal for continuous numeric variables and represent the straight line distance in a multi-dimensional space. Manhattan distance, also known as L1 distance, is a sum the absolute difference of a feature values. The metric is appropriate when the movement is constrained to a grid-like path, such as city blocks. Minkowski distance, a generalized metric that includes the both Euclidean and Manhattan, has a special case with the parameter b controlling the norm. So you can see the formula when P1 is it is a Manhattan, when P2 is Euclidean. Hammering distance. The measures the number of features positions where two category strings differ. It is used primarily for categorizing and binary, especially in text processing or genetic sequence. Choosing the right distance metric is crucial and depending on the type of the feature, scale, and the problem context. For example, Euclidean distance suits the continuous feature, while having distance fits the categorical data. Normalizing data before distance calculation can also improve the performance by preventing proportionally large features values from dominating the metric. Choosing the right value of K. The parameter K representing the number of neighbors taken into account for prediction directly impact the performance and behavior of the KNN model. Selecting an optimal K balances the bias and the variance of the model prediction. The smaller K103 leads to a model sensitive to noise, creating a jargoned decision boundaries and potentially overfitting conversely. Large K smooth the decision boundaries but risk overlooking the subtle patterns and resulting in underfitting. Odd values of Ks are commonly preferred in classification tasks to reduce the likelihood of its tie votes. Among neighbors, for example, having K5 helps us ensure the majority classes assessment clearly emerge. One recommended approach to find the best K fault across validation, where the dataset is split into K subsets and the model is evaluated iteratively and on the first source. The method offers robust performance estimates and help to avoid overfitting. A heuristic to starting turning K is the square root of the numbers of the training sample, and which usually provides reasonable initial guess. KNN for classification. KNN is a particularly powerful in classification problems such as predicting customer churn based on the demographic and user behavior. Considering a dataset containing customer age, income, and service usage patterns, and with a child labeled yes or no. In this example, given a new customer feature, the algorithm calculates distance to all existing customers and identifies the K closest neighbors. Through the majority voting among these neighbors, churn status is assigned to a prediction whether the new customer is likely to churn. The K constructs decision boundaries derived from the distribution and approximately of the data points. Unlike the parameter classification that inferred explicit boundaries, KNN generates flexible and non-linear boundaries that adapt dynamically to trained data. This property allows to model complex classes so the KNN construct this decision boundaries derived from the distribution and approximity of the data points. Unlike the parametric classifiers, the infer explicit boundaries KNN generate the flexible and non-linear boundaries that adapt dynamically to our training data. These properties allow us to model complex class separation but also makes the boundary sensitive to noise and feature scaling. Majority voting is a fundamental principle within KNN classification, where the class having the most neighbors vote determines a assigned label. Extensions include weight voting to give closest neighbors more information. KNN for regression. KNN algorithm is equally applicable for regression tasks where the goal is to predict the continuous outcome. For an instance, in real estate, one might use KNN to predict the house price based on features like square footage, number of bedrooms, and location. Given a new property, the algorithm identifies the K most similar houses in the dataset by computing distance using the appropriate metric. Instead of voting on the district classes, KNN regression calculate the average value of the target variable and house prices from these neighbors to estimate the new housing price. The weighted averaging techniques further refine predictions by assigning a greater influence to neighbors closer in the feature space, thereby reflecting institutions that provide more relevant information. This approach helps the model adapt and its estimation smoother to a local variation within the data. KNN regression is especially useful when relations between features and the target are complex and because it's minimal assumption. However, care must be taken into pre-processing data properly and selecting parameters to avoid overfitting the noisy predictions. The advantages and disadvantages. KNN offers several compiling advantages. Simple to understand and implement, is algorithmic basic, is intuitive and easy to code, making it accessible for beginners and quick prototyping. Versatile. KNN manually handles both classification and regression without needing separate model classification architecture. non-parametric. It is no assumption about the data distribution, adapting flexibility to diverse the dataset and complex boundaries. Despite this strength, KNN also present challenges computational cost. During prediction, KNN must compute distance to all the training points, which becomes costly with a larger dataset. Sensitive to irrelevant features without careful feature selections or scaling noisy or relevant, and scalability of issues. And overall, the KNN remains an effective tool when computational resources permit, and it is interruptibility and the adaptability make it foundation technique for machine learning. Thank you.